I am Francesca Noardo from the 3D GeoInformation Group at TU Delft. Here I will present the main results of the ISPRS Scientific Initiative 2019, the GeoBIM benchmark. After an introduction about the benchmark, I will show the specific tasks and, finally, the learned conclusions. To use and integrate building information models and 3D city models, interoperability is essential. For this reason, the standards were developed, in particular Industry Foundation classes by BuildingSmart and CityGML by OGC. However, how are these supported by tools, and are users able to use their potential effectively? The GeoBIM benchmark initiative, funded by ISPRS and EuroSDR, intended to answer this question. External participants were invited in order to consider the highest possible number of tools from different points of view. We defined 4 tasks to be tested. First is support for IFC within software. Second task is what options for georeferencing IFC files are available. Third task, what is the support for CityGML within software. And finally, conversions from IFC to CityGML and the other way around. These are the IFC and CityGML datasets provided to participants in order to make the tests. They were intended to cover several different aspects of possible issues of the study standards. Let's start with task 1 and 3, support for IFC and for CityGML. We treat them together since they were conceived in parallel. For these tasks, the participants were supposed to import the datasets in the tested software and, following instructions in online forms, check how it was able to read georeferencing, semantics, and geometry, and what functionalities were enabled with the standardized data. At the end, they had to deliver their observations together with the file re-exported to the standard format. After the end of the benchmark, we collected the participants' observations in synthesis tables, allowing a better reading and interpretation of results, and we analyzed the delivered models. We used both a more qualitative manual inspection within 3D viewers and a quantitative count of objects with the help of analysis tools. These are the results of the first check on the participants' answers. We can see how the scores are seldom 100%, mostly in visualization. ETL tools generally perform better, as well as 3D viewers, while some loss in semantics or geometry is often reported for GIS and BIM software. We also notice the discrepancy between the scores about the ability of software to correctly read and interpret the data and their functionalities for editing, querying, and analyzing them. When we look at a more quantitative analysis, comparing the number of the IFC objects in the exported models with the input ones, we see that many entities are added and many are lost. Only few software are able to keep the file unchanged. Some difference with the input models were also well visible in the 3D view of the exported models, and the same gain and loss of objects happen in the task 3 case with CityGML. Few software left the file completely unchanged. So, IFC and CityGML are potentially very powerful to support data exchange and analysis. However, this unreliability that we could see can hinder this potential. These results are an evidence that can be a reference to improve the standard, their use by the modelers, and their implementation in software. The main need we could see were about stating simple and clear structures and rules in standards. Task 2 investigates the available options to georeference IFC files. Participants had to georeference the files within the tool and deliver it together with a description of the process. In the post-processing, we refer to the levels of georeferencing as described by this paper by Clement and Gurney, and we checked how georeferencing information was stored within the delivered models with respect to this. Just a quick look at the levels of georeferencing. Different options are the use of attributes within IFC site, referring to geodetic coordinates for the level 20, the storage of a Cartesian point in a projected system associated either to ISC site or to the whole project, levels 30 and 40, and the use of the more advanced possibilities given by ISC version 4 for the level 50. In the delivered models, we see that often a level 30 is reached, implying a projected system to be used, which is good. However, we observe that such storage rules are not always consistently followed among northeast coordinates, height values, and rotation. So different parameters can follow different levels of georeferencing. In addition, in some cases, the same software stores georeferencing in different files according to different criteria. So we could see that there are valid options to store georeferencing. The flow is mainly in the choice and control by the user on how to store it. Since in some cases the accuracy of different levels can be similar, the preference should be decided according to the tools and the applications using them. Finally, task 4 is about conversions between CityGML and ISC in both directions. Like in the task 2, participants had to make the conversion, describe the processing, and deliver the converted model. In the post-processing phase, we analyze the models in 3D viewers and by means of validation tools when available. Two aspects of integration have to be considered in conversion. First is interoperability, that means that a valid model has to be produced. And second is harmonization, that is, the characteristics of the converted file have to comply with the ones of the destination models, which are here summarized in the table. We see first the results of conversion IFC to CityGML. The dataset representing IFC geometries allow the validation of the output and the check of the behavior of each type of geometry. We see that the conversion of this set of very different geometry storage options in IFC results in their unique storage as LOD4 geometry as generic city object, or in the other case, or LOD4 solids as building, with the only exception of the yellow one, which was a boundary surface representation also in the original model. Moreover, some kinds of geometries are not converted at all, as we see in the orange box. The components of buildings models are usually converted to generic city objects with LOD4 geometry. And here in the images we can see the best efforts considering both interoperability and harmonization. They use two FME workspaces to convert this model to an LOD4 model in one case, in CityGML, that is including inside and all the elements, and in the other case to a more generalized LOD3, so only exterior. We can see in the picture how the management of a generalized geometry is, however, challenging in the picture on the right. The results of conversion CityGML to ISC show similar results in the sense that everything is usually correctly mapped to the corresponding IFC entities, but little processing is made towards a change in the representation paradigm. A complex workflow is necessary to successfully convert from one format to the other one, and to change the representation paradigm too, allowing also harmonization, possibly in collaboration with the field experts. To conclude, the voluntary participation allowed to cover more software and to join a higher variety of skills. We integrated the tests to reach a higher coverage of tools. To improve the current situation, it is necessary to provide more explicit constraints within standards, together with clear validity criteria, preferably in accordance with use cases' needs. In addition, it is necessary the users to be more aware of the choose standards to better control the allowed options for storage and management. A critical step consists in the alignment between research, application fields and stakeholders, standardization organizations, and the implementation world. If you would like to read more details about the study, you can also read these papers or go to our website. And thank you for your attention.